Alright, so welcome to your first physics video. This will get us started on our study of speed and velocity, how things move, what I'm calling the constant velocity particle model, right, as our topic. That's what we're working with right now. Goals for this video, I want to introduce some terms, right, get you guys familiar with some vocab that we'll be working with, so that we can translate that into some equations. When we talk about terms, it's going to be really helpful if you have that cheat sheet that I gave you out. You can fill that out, right? Fill in the different definitions for terms, different symbols that are used for terms. Really, really helpful. Second thing that I want to do is talk about, how do we represent motion, right? How do physicists talk about motion? How do we communicate to other people how an object or a particle is moving, okay? Lots of different fun ways that you can communicate motion and things like that. But stick with me through the terms. They can get a little hairy, but do your best, all right? All of this is covered in chapter 2 of your book, so if you are confused on something, give that a gander. It'll help you out a little bit, all right? So, as we get going, 4 main terms that I want to define today: speed, velocity, position, and displacement, right? You've probably seen speed and velocity talked about before in previous math classes, right? Have you ever seen, a problem, right, maybe in an algebra class where it's like, Sally walks to school every day, right? There's Sally. Okay, it's 20 miles. She got a long walk, so she's got 20 miles to cover. And it takes her 1 hour to walk to school every day, right? She has to leave super early to get to school, but she likes to get her exercise, so she walks the hour to school every day over those 20 miles, right? Maybe at some point in your life, someone gave you this problem and said, how fast does Sally walk, right? How fast does she walk? Okay, and you probably gave an answer, something like, Sally walks 20 miles per hour, right? You looked at that and you said, okay, she goes 20 miles and it takes her 1 hour. I'm going to divide that. Some crazy math going on here. 20 divided by 1. So we've got 20 miles every hour, right? This is hopefully not foreign to you. Maybe you've seen something like this before. You just solved for Sally's speed, right? You gave us how fast she was going, okay? So let's start there, all right? Speed is a magnitude, right? It's got size, right? Right? It's some value that tells you how much distance, right, someone can cover in a unit time, right? So it's a distance, sorry for my chicken scratch, it's just part of the game, distance per time, right? You see this all the time, right? Driving on the highway, you have a speed limit, right? Miles per hour, kilometers per hour, whatever it might be, meters per second, right? Meters per second is the standard unit for speed. It's the one that we'll be seeing the most of in physics, right? So pay attention to that. Speed, when we use it in equations, we like to give it a little symbol, kind of like a variable in algebra, so that you don't have to write out speed. We usually do kind of like a loopy V. Not like a regular V, but sort of like a cursive V with a little tail. The reason we do that is you don't actually see speed all that often in equations. Most of the time we'll be working with velocities. So speed can have kind of a wonky letter because we don't use it all that often. Then we've got velocity, okay? A lot of times we use these words interchangeably, but they are not the same, all right? Speed and velocity are not the same. Related, but not the same. Velocity is going to have a magnitude, right? It's going to have some size, right? We could say that their velocity was 60 miles an hour, but it's also going to have direction, okay? And that's what makes it different from speed, right? It's going to indicate where that person was going, right? So in our example with Sally, her speed was 20 miles an hour. Her velocity was 20 miles an hour towards school, right? Let that sink in for a second, right? If, they give you speed limits on the highway, but they don't tell you what direction you need to do that speed in, right? They don't give you a velocity limit, right? If I said I was going 60 miles an hour, right, I would be giving a speed, but if I said I was going 60 miles an hour northwest, I would be giving a velocity, all right? So velocities have magnitude and direction. Same thing with speed, though. It tells you not only what direction you're going, but what distance you can cover in what amount of time. So similar units here. We're still going to see meters per second, right? Miles per hour, but with something that's denoting what direction we're going in, okay? And the symbol for velocity is just a regular old v, right? And we actually see this in equations a lot more often, which is why we use just a normal v. Makes our lives a lot simpler, okay? Quick little vocab word for you guys. Values like speed that just have magnitude, they don't have magnitude and direction, are called scalar values, okay? Speed is a scalar value, right? Velocity, because it has a direction, is called a vector. It's a vector quantity, all right? The reason we call velocity a vector quantity is that we can represent it with this thing called a vector, right? Which is basically a fancy word for an arrow, right? So if I was going 60 miles an hour northwest, right, if you can imagine this is a compass here, right down in your corner, right, I could represent that with an arrow, right? That would be my vector quantity, right? If I said I was just going 60 miles an hour, but didn't give you a direction which way I was going, can't represent that with a vector, all right? So keep these in mind, scalar and vector. We're going to be seeing this all semester, right? But just keep that in the back of your mind. All right. Last two vocab words for today, right? We're going to have position. Okay. And this seems simple, right? It's just going to be where you are in the world, right? Where is this object, right? But position can be kind of tricky to define, right? How do I tell you where you are, right? How do I tell, a bee that I'm tracking its velocity where it is, right? So position for now we're going to think of in one dimension, okay? And what this means is we're just working on a number line, right? So if you imagine that everything is happening here on a number line, right? Any object, particle that we talk about is moving along a number line. All right, we're going to have an origin, right? 0, that's what we call the origin, right? And then we're going to have some numbers. We're going to have positive numbers and we're going to have negative numbers, right? Right? And this is just going to tell us where in space we are, right? So if I'm at position 1, I'm right here, right? If I'm at position -3, I'm over here. We're not concerned with vertical position yet. We'll get there, but for now we're just doing one dimension, right? Right along a number line, okay? The symbol for position is just an X, okay? Right, position is just an X. All right, Our last term for today, displacement. Right? This is the change in position due to some velocity. Or movement, right? Okay, so say instead of, randomly placing myself at 1 on the number line and -3 on the number line, I moved from 1 to 3. Okay, I moved from 1 to 3. In that case, my displacement, right, is the distance between -3 and 1. Okay, the symbol for displacement is delta, right, this little triangle, x, right? Generally in science, the delta means change, x, so displacement is change in position. Okay, so there are going to be some other vocab words that we'll talk about in class next time, but let's start there. All right, so those are our 4 big vocab words for today. Let's talk quickly about representations of motion. Right? How is this motion going to represent? Okay. 2 big ways to represent motion. The first one is going to be a thing called motion maps. Okay. These are pretty cool. These might be my favorite representation of motion. Not super practical, but a cool skill to know. And the second is going to be a simple position versus time graph. Okay, this is going to look familiar if you've had any algebra, right? But we'll talk about that when we get there. So let's start off with a motion map. Okay, our motion maps, right, are going to happen on a number line, basically, right? You're going to draw a nice line, right? And you're going to be tracking the motion of an object. So let's say that it's a car, right? And the car starts on this side of the number line, right? We're not going to put numbers on it, but there's our car, right? And that car is in theory moving, right? Say it's moving this direction, okay? We are going to take a mental snapshot of that car every second, okay? So say at the first second, it's in this location right here that I've just drawn it, right? We wait a second, we take another picture. Now it's over here. Okay. Still moving this way as far as we can tell. One more second, we wait, take another picture, and our car is over here. Okay. The next step in making our motion map, right, is to take this car and say, I don't really want to treat this as a car. I'm going to simplify this into a particle. Okay. So you're going to pick a location on this car that you're going to track for each second, right? It has to be the same location. So I'm going to pick the front of the car, right? And I'm going to kind of bring that down and draw a little dot wherever that lands on each second, right? I can't pick the front of the car on one of my cars and then pick the back of the car on another one. That's not going to work, right? I've got to use the front of the car each time, right? Cool. And then we erase our cars, right? And we end up with a map of motion, right? To the non-physicist, right, this just looks like a line with dots under it, right? But because I've told you that it's a motion map, right, you should know that in between each of these dots is 1 second of movement, right? So let's look at another one of these. Okay. Say you've got a runner, right? And they're accelerating. This guy's got some problems with his arms. We'll ignore that for now. Right, so he starts off nice and slow, and then he gets faster, right? Remember, each of these images is 1 second apart, right? And then at the end of his run, right, we're moving this way. At the end of his run, he gets tired, so he hangs out here for a second, right? So he's just in the same place for a second. And then he decides he's going to walk back to where he started, right? So each second afterwards, he's just kind of walking back, right? This may seem complicated, but we can show this on our motion map, right? Again, we've got to pick the same location on each of our little men. I'm just going to pick his front foot, right, and draw a dot for each second. Okay, pretty straightforward, but once we get here, right, he stayed still for a second. So all we need to do is draw a second dot underneath, okay? And then when he starts walking back, we'll go ahead and draw dots again, right? Maybe you want to add some arrows just to indicate what direction he's going in, right, so that we don't get confused. But there you go. There's your motion map. All right? We're going to do more on these in class, but I wanted you to get a feel for them. Your book also does a great job explaining motion maps, so if you're confused, please just go ahead and take a look at that book, and we'll do more in class. All right? Last thing I want to quickly just show you position versus time graphs. This is going to be wicked quick. Right, in this case, we're just going to have a graphical representation, right? Position is going to be on our y-axis. Don't get confused, I'm going to write x because remember, x is the variable that denotes position, right? But that's on our vertical axis, okay? And time is going to be on our horizontal axis, right? So, give us some time values, right? And some positions. Notice I've included some spots for some negative positions because that can happen. Remember, we're on a number line, right? And say our car that we're watching starts at time 0 at the origin, so it's at position 0. Then by the first second, it's at position 2, right? So we go over to 1 second, up to position 2, add another point there, right? So you can plot the position, right? For example, after 2 seconds, if it was at position 3, right, we'd plot another point. Maybe it hangs out at position 3 for another, few seconds, and then turns around and drives back to position 2, right? We can just sort of connect these dots and graph a nice little line there, right? So now we have a nice visual representation of the motion of that car, right? Much easier than saying, okay, this car started out going pretty fast, it went from 0 to 2, then it went from 2 to 3, then it stood still for a little bit, and then it turned around and went back, right? We can just show someone this picture, and they've got all the information they need, all right? Make sure that you take a peek at the data that we collected in class today. There are some follow-up questions, pretty brief on that I want you guys to answer and submit on the portal. And other than that, we'll get going on this tomorrow.